The sun was the first source of energy for humans and, with some effort, maybe the last one we ever need. In 6 hours, a good desert can store more solar energy than the entire planet uses in a year. My body has a surface size of around 1.5 meters square. I could generate roughly 1,500 watts of solar power if I lazed in the sun all day, every day for a year. And look at this, the majority of the energy that we as humans used in the past came from the sun. Coal is nothing more than the fossilized remains of long-dead plants and animals that were powered by the sun when they were alive. Natural gas and oil, same stuff, the sun. One of our two sources of energy that isn't initially solar energy is nuclear power, which accounts for around 20% of our total energy production. The other is tidal energy, which the moon generates. In order to generate hydroelectric power, water must travel through rivers and up mountains where it is evaporating from the ocean due to solar energy. As you may have gathered by now, the sun is the source of all weather on our world. All of those species that we burn in biomass power plants, including trees, maize husks, and other biomass, once derived their energy from the sun. And last, there is direct solar power, which does indeed bypass all middlemen and derives its energy directly from the sun. Consequently, it must be more effective, right? It turns out that it is more effective, and while you might assume that something that is more effective would also be less expensive, this is not the case. Typically, photovoltaic cells, those large blue panels that people install on their roofs to produce electricity, come to mind when we think about solar power. I was genuinely startled to learn that the photoelectric effect has been understood for about 200 years while doing research for this. It was discovered in 1839 by a 19-year-old boy called Edmund Becquerel. This is so fascinating that I'm going to absolutely go off topic. We refer to Edmund Becquerel as a member of a scientific dynasty. The photoelectric effect was so discovered by Edmund Becquerel. With the help of electrolysis, his father discovered how to refine ores into their pure metals, and his son, along with Marie and Pierre Curie, discovered radioactivity. Just the fact that there can be so much scientific talent passed down from generation to generation within one family intrigues me. It is comparable to Martin and Charlie Sheen, but cooler and more grounded in science. The most costly solar cells that we have, however, tend to wind up in space since efficiency is expensive. However, when dealing with the International Space Station, it doesn't really matter how expensive anything is because you can't really connect a line up to it. The International Space Station features 16 solar wings that are 115 feet long. These solar panels can generate a whopping 120 kilowatts of power when used collectively. And now that you've been filled with an insatiable desire to learn more about solar panels, I can tell just by gazing into your eyes. Therefore, some of the electrons on a wafer of polysilicon will be knocked off and become free electrons if you hit it with light. This is something that is usual, but it doesn't even come close to the power required to build a solar panel. However, scientists and engineers discovered that if you dope silicon, a technical phrase that simply refers to contaminating it with impurities, with phosphorus, it suddenly has much too many electrons, giving you what is known as N-type silicon, N because it is negative. After that, if you take another silicon wafer and dope it with boron, it won't have enough electrons, and you'll end up with P-type silicon, which stands for positive. A conventional solar panel is just two layers of silicon, one of N-type and one of P-type, sandwiched on top of one another and linked by a conductor that we refer to as a wire. Depending on the size of the solar panel, you could power a calculator, a house, or a freaking space station if you placed anything on top of that wire. The challenge is finding new, less expensive materials that can be used to make photovoltaic panels, or improving solar panels' efficiency so that they can offset their high costs. Now I have to veer somewhat off subject and discuss how solar power provides a benefit that not many people are aware of. In general, humankind generates energy at enormous power plants that are frequently hundreds of kilometers from the actual point of usage. It costs a lot of money to build these enormous transmission lines to carry the electricity from the power plant to your home, and it is also not very efficient for the electricity to travel such a long distance. Simply moving the energy from one area to another can result in losses of up to 30%, which is humiliating. All those megatons of carbon dioxide were produced only for the purpose of dissipating electricity while doing so. There is a reason for this, and that is that having one large coal-fired power station in one location allows for pollution management and maximum efficiency rather than a number of smaller, less effective ones dispersed over the terrain. However, with solar energy, you can really produce the energy right where it is needed. You may place the panel on your roof and use it in your house. It's excellent and is what we refer to as distributed power. There are times when it makes sense to utilize solar energy centrally, with vast fields covered with solar panels, particularly in locations where the sun shines for 364 days out of the year. But before you get too enthusiastic, solar panels still cost far more than centralized power plants, despite the dispersed energy's amazing efficiency. Photovoltaic panels are already spread across rooftops all over the world, yet despite their ecological benefits, they are still not economically viable. We still rely heavily on coal and natural gas for the majority of our electricity needs because it is practically impossible to get a good value for your money from solar panels. Even today, burning wood produces more energy than solar panels do. You tell yourself that there must be a better way to accomplish this. Perhaps there is, too. If you were a really evil or scientifically inclined youngster, you might have tried this method in the past, using your magnifying glass to generate power, and you were probably using that power to kill little insects, which I do not condone, but there you have it. I would prefer if we used that work to drive electrons into your home so you could watch me on your computer screen rather than to use it to evaporate little creatures. Sunlight carries a lot of energy, and if you concentrate it in one spot, you can accomplish a lot of work. We utilize mirrors instead of lenses because they are far less costly and may be used in solar power facilities. There are two main approaches to focus light in these so-called concentrating solar power plants. In general, we employ mirrors to direct light toward a single point. One method involves constructing a massive tower, filling a field with mirrors, and ensuring that the sun is always focused on the top of the tower by means of the mirrors. Building a massive tower that can withstand being heated to absurd temperatures is rather expensive, but it is less expensive than using pure photovoltaic. The other method of concentrating solar energy involves the construction of enormous mirror-like half-cylinders, or parabolic troughs, with a pipe in the middle. By the time the oil has passed through the parabolic trough, it is so hot that it immediately vaporizes when it comes in contact with water, which is how power plants typically operate because the vapor takes up much more space than the liquid does. Even yet, concentrated solar power plants only manage to generate electricity at best for around 11 cents per kilowatt hour, which is almost twice as costly as a natural gas power plant. But wait a minute, now we've got two solar options. One is photovoltaics, where the most expensive component is energy capture, and the other is concentrated solar power, where the most expensive component is energy conversion to electricity. What if we could combine the greatest aspects of each of these technologies? As it turns out, we can, and this may be the only way to make solar energy economically viable in our energy market. Engineers and scientists are employing mirrors to focus light on extremely tiny solar cells using extremely sophisticated photovoltaic cells that can absorb far more electricity than the one in your calculator. The solar panel is now absorbing 10 times more sunlight and providing 10 times more energy, but the solar panel itself, the priciest component, remains the same size. This is because the mirrors, which are really collecting the light, are 10 times bigger than the solar panel. This method, which we refer to as concentrated photovoltaics, allows us to produce the most economical type of solar energy currently available. Concentrated photovoltaics, or CPV, is what they name it, and many gigawatts of it are about to be online in the next 10 years. A gigawatt is a significant amount of electricity. It is about equivalent to the output of the biggest nuclear power reactors in America. It doesn't matter how expensive the panels on the space station are because there is no other way to get power up there. I'll return to the space station for a moment, mainly just to show more of the awesome graphics of the space station. Now, I kind of lied to you when I stated that those solar panels generate roughly 120 kilowatts of power. Because the space station is under the shadow of the Earth, its solar panels are producing 0 watts of power about half the time. And on Earth, from where we are standing, we refer to that shadow as nighttime, which is the enemy of solar power. And therefore, it would appear that solar power could never supply 100% of our energy demands. Whether it's coal, nuclear, or natural gas, we'll always need something else to keep the lights on at night. Except if we could figure out a method to store the energy during the day and then release it all at night. It turns out that we can, sort of. We can use pumps to move it up hills, and at night, we can let the water fall through turbines to produce electricity. Alternately, we might pressurize enormous, enclosed earthly tunnels to hundreds of psi throughout the day and then allow the air escape to produce power. To boil water at night, we can dissolve salt by heating it until it becomes liquid. Alternately, we can split water using solar energy during the day into hydrogen and oxygen, then use the hydrogen in fuel cells at night to produce electricity. Unfortunately, solar energy is already quite costly, and each of these methods for storing it makes it much more expensive. Therefore, even though it is possible and we have developed the answers, they cannot be implemented anytime soon. The law of conservation of energy, which states that you can never get more energy out of a system than you put in, is a fundamental tenet of physics. Since individuals won't put in more effort than necessary to do a certain amount of labor, there may as well be a law of conservation of dollars in economics. If a mountain has a tunnel already dug through it, why would I climb over it? Aside from the apparent truth that every year, that tunnel emits hundreds of megatons of carbon dioxide and other pollutants into the environment, the largest power plants in America, meanwhile, generate about 1,000 megawatts of electricity. Solar power is wonderful, and I hope you learned something. If we had 116 billion of those, it would just be enough to match the amount of power that the sun pours down on our small globe every single day. Don't forget to click the subscribe and bell icon.